For transformations, the type of question I like to ask on a test is this type, where I give you the parent function and describe transformations and you write the formula. I think that's a good way to make sure that you know the relationship between the functions, the formulas, and the transformations. So for the following exercises, write a formula for the function obtained when the graph is shifted as described. So I'm going to do a couple of these. Number 6 here, f of x is the square root of x, and we're going to shift that up 1 and to the left 2 units. So I'm going to go step by step here on this one. So if we wanted to shift it up 1, we would add 1 to the formula. If you want to shift the graph up by c, you add c. If you want to go down, you subtract c. So if we take square root of x plus 1, that would move it up 1. If we wanted to go to the left, that's going to be inside. We need to add or subtract to x on the inside. And these are always backwards. Horizontal shifts are backwards. If you want to go to the left, toward the negative side of the number line, you actually have to add. So I put a plus 2, I replace x with x plus 2. So we get y equals square root of x plus 2 plus 1. And we can't combine the 2 and the 1 because one's inside, one's outside. So there's what we would get, square root of x plus 2 plus 1. Okay, let me do another one. We got the graph of 1 over x, and we're going to vertically stretch it by a factor of 8, and then shift it to the right 4 units and up 2 units. So again, I'm going to go one step at a time. If I want to vertically stretch something by 8, then I multiply the y values by 8. So I multiply the formula by 8. So y would be 8 times 1 over x, which if I wanted, I could write as 8 over x. I'm going to do that. And then we want to shift it to the right by 4. So again, the horizontal shift, you replace x with x plus or minus the number, and opposite direction of what we think at first. Plus side of the number line, you actually need a minus to get you there. So we replace x with x minus 4 to go to the right. So we get 8 over x minus 4. So that's vertically stretched by 8 and shifted to the right 4. And then up 2, I just add 2 to the whole formula. So we get y is 8 over x minus 4 plus 2. And then we did inverses. For inverses, you want to be able to find a formula for an inverse. And I'm going to do a couple here, and you want to be able to draw a graph for an inverse. Do that in a second. So depends on the type of function you have. The basic steps are take it out of function notation and swap x and y and solve for y. It depends on the function as to what it takes to solve for y. So on number 42, I've gone ahead and swapped the letters here. You'd have y equals 3 over x minus 2, but I'm going to swap x and y and get x equals 3 over y minus 2. And I need to solve that for y. Here I could multiply both sides by y minus 2 to get rid of the fraction. And on one side we'd just be left with 3, and on the other side we have x times y minus 2. Now we could distribute, but we're trying to solve for y, so I'm going to go ahead and divide by x. And I get y minus 2 equals 3 over x. And then I add 2. And there we go. Y is 3 over x plus 2. That would be my inverse. I could use the inverse notation if I wanted. F to the negative 1. F inverse is 3 over x plus 2. And then the one with the cube power, we're going to get a cubed root somewhere in our answer. So we've got y equals x to the third minus 1. Swap x and y. So x equals y to the third minus 1. Add 1 to both sides. We've got x plus 1 equals y to the third. Take the cubed root. Y is the cubed root of x plus 1, and that's my inverse function. The cubed root of x, the inverse of x cubed minus 1 is the cubed root of x plus 1. Graphs. The way to think about graphs, if you were to make a set of points for this function, its inverse, you would swap the x's and y's. You can actually do that point-wise. So I've made a very small table here. There's just a couple of points that hit right on, and then we could use the shape here. So this graph goes through 2, 0, and 6, 2, among lots of other points here, infinitely many other points, but those are 2 that hit right on the grid. So the inverse, I would swap the x's and y's. Instead of 2, 0, it would go through 0, 2. Instead of 6, 2, it would go through 2, 6. So that's 2 points I could plot. 2, 0, or instead of 2, 0, I got 0, 2, and then we've got 2, 6, 2, 6. And then think about it being the reflection across the line y equals x, so I just draw my shape reflected through those points. So make yourself enough points, take enough points from, in this case, the green graph, my original graph, swap the x's and y's and plot those and draw your curve in, and what you get should be a mirror image across y equals x. And then we got quadratics. Let's finish off a few examples here on quadratics. For quadratics, you want to be able to graph them, which includes finding all the important features. You want to be able to find x and y intercepts, the vertex. Sometimes you need a couple of extra points. So for this one, we've got f of x is negative x squared plus 4x plus 3. So you could have one in that general form, ax squared plus bx plus c. If you want the y-intercept, you just plug in 0. In this case, you'll get just 3 is all that's left. The terms with x go away when you plug in 0. For the vertex in this form, we can use the formula that the x-coordinate is at negative b over 2a. Similar to the quadratic formula without the discriminant part. You get negative b over 2a will be where the vertex is located. So that's negative, in this case, 4 over negative 2. 2 times negative 1. So you wind up with positive 2. Okay, you got 4 over negative 2, but it's the opposite sign of that. And then you plug that in to get the y value. So you get negative 2 squared will be negative 4 plus 4 times 2 will be 8 plus 3. And compute that out and you get 7. So my vertex is 2, 7. For the x-intercepts, we have to solve the quadratic equation. And I usually find the vertex first and think about whether or not it's going to have x-intercepts. If you have imaginary answers, there's no x-intercepts, so we don't even have to bother with them. This one does have x-intercepts, though. It's got a negative coefficient in front, so it's a parabola that opens down, and the vertex is in quadrant 1, 2, 7. It's positive and opens down. It will hit the axis. So we could use the quadratic formula, or we could factor. This one you have to use the quadratic formula. You get irrational answers. So we could do negative b plus or minus the square root of b squared minus 4ac over 2a. So we got to know our quadratic formula. If you work that out, you get negative 4 plus or minus square root of 28 over negative 2. Square root of 28 is irrational, and we're trying to graph this thing, so I'm going to go ahead and get decimal answers. I punched them in my calculator and got approximately negative 0.65 and 4.65, which is definitely accurate enough to draw a graph. Okay, so I'm going to plot everything I know now. I've got a y-intercept at 3. I have x-intercepts at about negative 0.65 and 4.65, and we have our vertex at 2, 7. And then I would just take my pencil and draw it in. I went ahead and did it with the computer there, but fill it in through those points. So find the vertex by finding negative b over 2a and plugging it in to get the y value. You can plug in 0 and get the y-intercept, and with the quadratic formula I can get the x-intercepts. And as long as I've got the vertex, you want to include the intercepts if you have them, but as long as you've got the vertex and 1 point on each side, that'll help you draw the correct width on the parabola there. Let's do one that's in the vertex form, or the standard form as a lot of books call it. So we've got f of x is negative 2 times x plus 3 squared minus 6. Again, I'm going to find the y-intercept first, plug in 0. It's a little more work this time. You don't just get all the first stuff to cancel out. We've got negative 2 times 0 plus 3 squared, so negative 2 times 3 squared minus 6, which works out to be negative 24, so I'm going to have to go beyond the standard window if I want to see that one. The vertex we can just see off of the formula. We think about transformations. This one's been reflected and stretched, but it's been shifted to the left by 3, so the x-coordinate will go to negative 3 and then down 6. Negative 3, negative 6 is the location of the vertex by transformations. And if you think about that, that's in quadrant 3. You've got negative coordinates, and it's opening down. It's not going to hit the x-axis. It will have no x-intercepts. You can set it equal to 0 and try to solve, and you'll wind up with square root of a negative number, and you won't get any x-intercepts. That means I need a couple more points. I always just pick a point on each side of the vertex. I've got the vertex at negative 3. I went 2 in each direction. Got negative 5, negative 1. Plug those in. Get negative 14 for each y value there if you plug them into the original function. Plot all of that stuff and you got enough points to draw your picture. You've got the vertex at negative 3, negative 6. I had to use a big enough scale here. I counted by tens in the y direction so I could show that y-intercept at 0, negative 24. And then again, I need at least 1 point on either side, so I picked a couple of x values, one on each side of my vertex, and got those 2 points, and then you can draw in your parabola with the correct width there. Okay, and then the last thing we want to do is a quadratic application. Looks like I forgot to animate that part of that one. But this type of application, we have something that's modeled by a quadratic function, and we want to find the maximum or the minimum as our big application we looked at in this section. And it has to be the vertex because of the shape. So we have a rocket launched into the air. Its height in meters above sea level as a function of time in seconds is given by this quadratic equation. H of t for the height at time t is negative 4.9 t squared plus 229 t plus 234. Find the maximum height the rocket obtains. So that's a parabola opening down. The vertex is the max. So the t-coordinate of the vertex, the input coordinate, is negative b over 2a. So for this problem, that's negative 229 over 2 times negative 4.9. And if you compute that, you get a long decimal number. I rounded it off. 23.37 seconds would be the units. It says our time is in seconds and our height is in meters. You then plug that in, which is what I already had here, but I get the t-coordinate by doing negative b over 2a to find the t-coordinate of the vertex. Plug it in and I'll have the maximum height, which winds up being about 2,909.56 meters, if I take a couple of decimal places there, or about 2910, 2,910 if you rounded to the nearest whole number.